Alrighty, so hopefully this works out well. It's going to bug the crap out of me, but hopefully the camera picks up my voice a little better. So for our warm-up, we're going to go through and find our missing transformation from C to D. And we're going to do so by going through and taking a look at the given information. One thing I want to ask you guys is I have the solutions available for each of the assignments. Do you want me to post them the day after they're due, just so that you can review them and stuff? Okay, so I'll get that done this afternoon. I was going to hold off because a number of people, well, not a number of people, several people did not turn in the assignment. But the thing is, at this point, the assignment is late, and since we're on a 6-week schedule, I just really don't have time to play catch-up for those few people that are getting themselves behind. One thing I'll strongly encourage you to do is make sure you stay caught up on your assignments and don't get behind, because with each of these assignments counting essentially as 1/6 of your grade, missing one is going to, have some very adverse effects on your grade if you don't get it turned in to me. Okay, so after the warm-up, we're going to go through and review the XYZ fixed angle transformation, followed by the ZYX Euler angle transformation. Both of these are just to allow us to interpret these three-dimensional spaces. As I've already mentioned, when we're defining a joint, we're going to define that joint along a single degree of freedom. And so these representations, while it will show up in our transformations, will not be defined as such. They won't necessarily show up as a fixed angle transformation. They'll just happen to show up as three rotational transformations that we could interpret as a fixed angle or an Euler angle transformation. And then finally, we're going to hopefully break out of Chapter 2, get into Chapter 3, and start talking about our lower pair descriptions and parameters, how we can go through and start characterizing the actual joints and links on our robot. So with that being said then, I'll give you guys a minute to go through and take a look at the warm-up, and then from there, we'll take a look at it to figure out how we could solve this. And by the way, we will use Thursday as an in-class lab day, give you guys a chance to go through and do problems 3 and 10 on the assignment. That way I'm here giving you a hand with it. Figure that way if you run into a situation where you're just not familiar enough with MATLAB and you need somebody to help you troubleshoot your code, I can give you a hand with it. Plus, on top of that, we are going into the holiday weekend, and while no one has indicated such right now, I do suspect that a few people anyhow will probably head out of town Thursday afternoon and probably not prioritize this class, so, or hopefully any other class. If you deprioritize my class, then I expect you to deprioritize them all. So what do you think here? How are we going to find the transformation from C to D?
Work backwards from...
Yeah, we can work backwards. Now we can probably cheat, right? Because we could probably say that 25 minus 17 plus the missing quantity in C, I'll call it X, plus, let's see, plus X is equal to 15, we could just say that this plus the missing x component out of here has to equal 15. And then we could probably go through and do something similar here. 15 minus 10 plus y is equal to 20, and so on and so forth. So we have a very low-tech way of figuring out what the information in that missing matrix should be. So I'll go ahead and write that down real quick. So we have 15 minus 10 plus y is equal to 20, and then 20 minus 10 plus z is equal to 10.
Is it plus 5?
Plus 5. Oh, right there, yeah. So plus 5 is equal to, plus z is equal to 10. Yeah, 10. So from here we see that x is going to be equal to what? Minus 10 plus 7, 27. Y will equal to 15. And let's see, that would be negative 10 minus 15. So you guys agree with that? All right, very well. Let me see it. Oh,
First
no,
one should equal 7,
Yeah.
7.
because you have 15 plus 17 minus 25 equals 7.
Okay, so 15 plus 17 minus, okay. And sure enough, that's 32 minus 25, so just equals 7. Okay, so this is very low tech. I mean, we could probably teach this to a bunch of 7th graders, right? How can we go through and make it look like we actually know our stuff? Or, I guess more importantly, how can we get MATLAB to do this for us?
Take the inverse of transform, is it B to C? So you want to go from C to B, add that from B to A, add that from A to D, and then you should go from.
Right. So, so we can go through and say that in order to find this, we can actually go backwards through it. So what I'm going to do is I'm going to go through and say that the transform from A to D is equal to the product of each of the subsequent transforms. So the transform from A to B times the transform from B to C times the transform from C to D. And in this case, I conveniently put the transform we were looking for at the end. So how can I peel off these two matrices here? Well, we can get rid of this first one. Ultimately, what we want to do is get this guy isolated, right? So we can peel off this first one by hitting both sides of the equal sign with its inverse. So we can go through and say that we have A to B invert times A to D, and that's going to equal, well, the inverse of the transform from A to B times the transform from A to B is going to be an identity. It's going to drop off. So this is going to equal transform from B to C times the transforms from C to D. And now what?
Do the same thing again.
Do the same thing again, peel off this second matrix, transform from B to C. And when we do so, we see that we end up with the transform from B to C inverted times the transform from A to B inverted times the transform from A to D, and that equals the transform from C to D. Now, in this case, are we going to run into an issue if we get these out of order?
Yeah.
Because they're translations, the math will turn out the same. The order we apply those translation vectors will be different, but the math will give us the same result. Now, when we would really want to pay attention to this is when we're missing or intermixing both translation and rotations within these transformations. In this case, we could probably get these out of order and not really have too much to concern about, but if we were to go through, is that too loud? Okay, good, so. So in this case, we could get these out of order, it wouldn't affect us too much, but the fact is we probably would, just out of good habit, we want to make sure that we're performing the math in the proper order. That makes sense? Okay, so with that then, we know that we need to take, and I'm going to erase this portion here. Hopefully you guys have that in your note if you intend it to be there. So we have the inverse of the transform from B to C. So what would that look like?
Isn't it just the B to C one, but just the sign switched on the
Yeah.
top right three?
That's exactly the case. The sign will be switched on the position vector because we're just going backwards through that transformation matrix. So 0, 1, 0, 0, 0, 1, 0, 0, 0, and then a positive 17, a positive 10, and a negative 5, just changing the sign on each of those quantities. And then how about the inverse of the transform from A to B?
Same thing.
Same thing. So we have negative 25 and negative 15 and negative 10. And then finally, hitting that with the transform from A to D, we have 1, 0, 0, 0, 1, 0, 0, 0, 1, bunch of zeros, and then 15, 20, and 10, 1 there. So let's see. Everyone would agree with that? So going on through here, we can go through and do the matrix multiplication if we want, but we know what the end effect will be. We have, let's see, 1 times a negative 25 plus a 0 plus a 0 plus 17, so a negative 25 plus 17 is a negative 8. Okay. Going through each of the rows. We would end up with a negative 8, followed by a 10 minus 15, which would be a negative 5, a 5 minus, negative 5 minus 10 would be a negative 15, and followed by a 1. You know, every time I do one of these examples on the board, about this step, I'm just hoping that it turns out the way we expect it to be, so. So let's see, we have 15 minus 8 is a 7, and I'm not, I guess just to make everyone happy, I will. So 15 minus 8 is 7. Okay, that's good. Let's see. Okay, how do I do this? Here we go. 20 minus 5, okay, is 15. Then we have 10 minus 15, oops. Let's see, we have 10 minus 15. Did I mess up there?
Is it a negative 10 or no?
Negative 20.
I don't know.
It's a negative 20.
So did I mess up here when I did that?
Down.
Here?
The negative 10 in the second, it should be negative 20.
Oh,
Yeah.
this should be a negative
No,
20.
no, 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 the negative 25, negative 15, negative 10, it should be a 20.
That should be a 20.
Yeah.
Okay, so then we have
negative 25, okay, yeah. That helps out, because then we know that we have 10 minus 25 is negative 15 that we're expecting.
So, we can go through and use some relatively simple algebra to go through and analyze this, which works out great. But ultimately, this is kind of the pattern that we want to start developing when we're thinking about this, because these transformations are what we'll be using throughout the rest of the course to set up the descriptions of our robot as we describe its motion in space. So.
And eventually that rotation matrix is gonna start changing.
Yeah, and that's actually what we're going to start looking at today, is implementing that rotation matrix into these frame references. What we can, or what we should be recognizing at this point, is the reason we're going with a 4x4 here is because this 4x4 matrix describes both the position and orientation of our frame. Okay, it's providing the position relative to some other frame and the rotation of that new frame relative to the original frame. So this is our frame description, and ideally that's what we're after. Now, one of the problems with this format is that we're introducing 12 parameters to describe the position and orientation of this frame. And that's a whole lot of parameters to keep track of. So what we'll do in chapter 3 is we'll go through and try to minimize those parameters. In fact, we can get the number of parameters we need down to 4. Okay? If we go through and make sure that we very carefully define each of the joint, or how we describe each joint and each connected link in a kinematic chain. That makes sense? Okay, so with that, then let's go through and real quick review the XYZ fixed angle transformations. If you recall, what this did, and let me bring up the representation, or I'll just sketch it up here on the board so we can move through it real quick. What we did with a XYZ fixed angle transformation is we started off with a base frame, and I'll draw my X, Y, and Z like this. This is my positive X, positive Y, and positive Z. What was the first thing we did when describing that X, Y, and Z? So the first thing we did was we described a rotation about the x-axis. So we went through and said, okay, well, the first thing we're going to do is describe a rotation about the x-axis, which results in a new frame that might look something like that. Since we're pointing our thumb along the right-hand rule, we would see that that, in fact, would represent a negative rotation. If I had put this vector back here, we could say that this is our new y prime, and this is our new z prime, and that would represent a positive rotation about at x. What was the next thing we did?
About Y.
About y. Which y?
What are you talking about? Are you talking about when we just did it across the Y-axis?
Right, but do we use this y or this y?
we're doing another transformation, that Y up there, if we're going from our original to
Okay, so this fixed term in this fixed angle transformation tells us that we're using the fixed frame that we're starting with. So when we're doing an XYZ fixed angle transformation, we're always referencing these transformations back to the original frame that we started with. In this case, we can consider the black frame our frame A. So what we would then do is do a rotation about our y-axis, and what we would see then is, let's see, what would that look like?
our C would go over to the right quadrant-ish, and our X would go up towards the Z quadrant.
Yeah, so kinda like that, and that. No, not like that, kinda like that.
Yeah.
So we can call this our, oh, actually, well, we'll run with it, so this would be our X double prime, our Z double prime, and our Y fellow prime.
And then what?
About our Z axis.
Let me think about this, just to make sure I'm doing, well, this is the way the description describes it, so. Then about our Z, and since we're going through and rotating this about our fixed Z, what we would then do is rotate this frame.
Something like, maybe something like that.
Okay. And this is kind of arbitrary, it's kind of hard to see, but ultimately what we're doing is we're starting off by rotating about the x-axis in our original frame, then performing a rotation about our y-axis in the original frame, and following that with a z rotation, or a rotation about z in the original frame. Okay, and that's very literally how the book describes this. It says that these fixed angle transformations rotate about the x-axis in the in frame A. Then rotate about the y-axis in frame A. And finally, rotate about the z-axis in frame A. What's unique about, what's unique about that description? Or how could we interpret this transformation? It is the transformation going from frame A to frame B. So when we're looking at these fixed angle transformations, we can think of these as the transformation from A to B. And in fact, we see that this XYZ transformation, we know has the three angles associated with it, the gamma, the beta, and the alpha. We list these in that particular order because we know that our alpha is rotating about the z-axis, our beta is rotating about the y-axis, and our gamma is rotating about the x-axis. That makes sense? So it is backwards from the way we would think about it, but it does make sense to us, hopefully. What's another way of interpreting this?
And keep in mind, once again, that this is just to help us kind of understand these joints with 3 degrees of freedom on them. In general, we will not go through and use this. We'll be using this as a series of single degree of freedom transformations. Well, the other way to think about this is looking at the transformation from B back to A, and that's where these Euler angle transformations come into play. By the way, in this case, we can write this very literally as it sits here. We're going to go through, and let me make sure I write this down properly. So we're going to do a rotation about Z by alpha, a rotation about Y of beta, and then a rotation about Z, about X out of gamma. Okay? Turns out that our Euler angle transformation is almost identical. The distinction is not what it's defined as, but rather how we're interpreting these transformations. So, in the Euler angle transformation, we end up with almost exactly, well, we end up with the exactly same transformation, but the order in which we interpret it is different. So we start with the with frame B coincident with frame A. That means it's sitting right there on top of it. And then we go through and say, we rotate frame B about the z-axis of frame B. Then we go through and rotate B about the y-axis of frame B. And finally, we rotate frame B about the x-axis of frame B. So the big distinction between these two representations is, in this case, we're referencing frame A in each of our transformations. In the Euler angle transformation, each of the subsequent transformations is with respect to the previous configuration of frame B. Does that make sense? Now, I believe mechanical engineering, you could correct me on this, but I believe in mechanical engineering you tend to use Euler angles much more frequently than what you do fixed angle representation. Is that correct?
I don't know, I haven't taken very many classes in the
Oh,
field yet.
okay. Well, at some point you'll have to come back and let me know if I'm full of crap or not, so. That's my understanding. I know that when I was sitting in Professor Pringle's class, he, in his statics class, he started talking about Euler angles about the time that I lost interest, so. So anyhow, you'll probably run into this idea of the Euler angle, or the Euler angle characteristics again. What's the nice thing about this? If we have our transformation setting here, and we have our rotation that is dependent on alpha, beta, and gamma, and then we have our position vector, what did we just do? How many parameters did we just have? We have 12. I don't have that many fingers. Okay, so just a moment ago we had 12 parameters. Now how many parameters do we have? Still have 12 numbers, but in fact, we now have it down to 6 parameters, which is really nice, because these 6 parameters can be used to describe this transformation. That takes us down from the 12 parameters we had just a moment ago. That makes sense? So the big reason why we would go through and define these transformations is hopefully to get to the point where we can reduce the number of parameters that we're using to describe each of the joint and link combinations. Okay, how many characteristics do you think we will ultimately get down, or how many parameters do you think we'll ultimately get down to? We'll get down to 4, okay? Because we need to know something about the location of that joint and the degree of freedom associated with that joint. So ultimately what we're going to do is get to the point where we can summarize this entire frame with 4 parameters, and we're well on our way to doing that. That makes sense? If we can minimize the number of parameters that we're dealing with, then we can minimize the amount of manipulation our program has to do in order to go through and control the robot. And that's key, particularly 20 years ago when they were trying to use low quality 8-bit microprocessors to control the robots. Good? Okay, so with that then, we're almost done with chapter 2. At this point, well, here in just a second, you'll be able to knock out the assignment for chapter 2 by reviewing your notes. The only other thing that we have to pick out at chapter 2 is how to determine the inverse of a homogeneous transformation. And in order to take a look at that, I will, before I go on, is there anything, any questions that you guys want to ask on this? Keep in mind that my drawing over there is pretty poor, so the diagram that's included in the notes, it was produced in MATLAB and is surprisingly better, so just bear with me there. Okay, so and I will go and erase that too. So let's say that we have a transformation from A to B. And we know that this transformation is going to be packaged as the rotation from A to B, the position vector pointing from, or to the origin of B, from A, and then a bunch of zeros and a 1. How are we going to invert that? We are trying to find the inverse of the transformation from A to B. So we're trying to find the transformation that takes us from B back to A. Is this, well, it is the inverse of the transformation from A to B, but is it the transpose? nice if it was. But is it? Where does that idea of transposes actually work? When is the inverse of a matrix equal to the transpose of it?
It's like when they're all perpendicular to each other.
Okay, when they're perpendicular and unit vectors, so when they're orthonormal. Okay, is this transformation matrix orthonormal? Up to this point, we could say yeah, but the problem is this last column may or may not be orthonormal in nature, right? This position vector can be of any length necessary in order to describe or displacement from one frame to the next. So in this case, we can't just go through and swap this diagonally, okay, in order to get this done. So that does not work. What we see though is that since this part of the matrix is orthonormal, we can go through and say that the transform from B to A, which is the inverse of the transform from A to B, is equal to the inverse or the transpose of the rotation matrix. And that makes sense to us because all we're doing is undoing the effects of that rotation matrix. This down here will remain the same because ultimately this last row is just holding our place value, giving us the 4x4 dimensionality that we need to make our math operations work out properly. What are we going to do with the displacement vector?
And we're not augmenting with the identity here.
What's that?
Or we're not finding the inverse by augmenting the matrix with an identity.
Well, we need to keep in mind what this is doing. Okay, so what is this doing when we're actually describing this transformation? So we have frame A here pointing at, which color will it be? Pointing at frame B there. Okay, what's the order of operations here? We describe the displacement and then we describe the rotation of that frame. That makes sense? So when we're going from frame A to frame B, this is frame A, this is frame B, we're describing first the displacement, then the rotation, of the frame. Okay? So how are we going to undo that? How are we going to describe the position from, or the position vector, or displacement vector from frame B back to frame A? Well, we're going to be going backwards, right? So there's definitely going to be a negative tossed in there. So it's going to be a big old fat negative. But what are we going to have to do first? So we provided displacement, then we rotated the frame. In order to undo this, we're going to have to first unrotate the frame and then provide the displacement. So we're going to have to go through and hit the position vector with the inverse rotation matrix and then by the position vector. So, yeah. And when we do so, what we'll see is that we will successfully undo the effects of a transformation. That makes sense? Okay, so then let's do a quick example, and we will, with that, officially be done with chapter 2 and be able to move into actual application of this stuff. And hopefully next week we'll get into our first real programming exercise that's going to be just designing a program to represent motion of a 2-axis, maybe a 3-axis planar robot. We'll kind of decide going into next week what we want to do. What do you guys want to do? And keep in mind that you have my help in class, unlike those people that don't show up.
What was the question again?
Do you want to, for your programming assignment next week, do you want to model a 2-axis planar robot, or I'm sorry, a 2-joint planar robot, or a 3-joint? So we'll think about it over the weekend and stuff, so.
I don't wanna be lynched.
Yeah. Well, you're on the wrong side of camera for that, they don't know who you are,
Oh, I
so,
think they'll figure it out.
awesome.
Push
Okay.
fingers on my record. Don't say it out loud.
Okay, so as our example, find the transformation from B to A if the transformation from A to B is equal to a cosine, 30 degrees, negative sine, 30 degrees, sine, 30 degrees, cosine, 30 degrees, 0, 0. And my position vector is really uninteresting, 5, 4, 3. So spend a few minutes finding the inverse of that matrix. And what does this inverse allow us to do? This would allow us to describe the forward kinematics. This would allow us to, this would allow us to describe the forward kinematics. This would allow us to describe the inverse kinematics. These hour-and-a-half classes really aren't too bad, are they? I thought that it was really going to be hard filling them up with material, but it's not too bad, actually.
It depends on the material. If
Yeah,
you were doing, the PLC lecture was a little bit rough.
yeah, that was kind of dry, though. I mean,
Hey,
that
it's still
stuff
better than
was,
linear algebra.
yeah, that, the lectures for PLC, that's just, I would almost prefer just to post that stuff online and spend the entire class in the lab, so it would almost work out better if that was the way it was arranged, so.
It depends. If people haven't had any exposure to like Boolean algebra, then they're just toast.
Yeah.
Like,
Well, the way that people want that class designed is so that they don't have to have any background with Boolean algebra, but that you don't spend any time developing an understanding of Boolean algebra. So it's kind of like a no-win situation, you know. You can't have them go through the class without working with Boolean algebra, but at the same time, in order to develop any understanding of it, in order to get through the material, it's just, you know, you're kind of fighting two sides of, you know, both sides of the battle there, so. Okay, so we're going to go through and try to invert this. So the easier part of this is just determining the inverse rotation matrix. So we're going to go through and define the transformation from B to A, and what's the inverse rotation matrix going to look like? Right here's our rotation matrix. So all we're going to do is hit that with a transpose operation. We're just going to flip it across that main diagonal. So we're going to have cosine of 30 degrees, sine of 30 degrees, 0, negative sine of 30 degrees, cosine 30 degrees, that guy's going left out, and then 0, 0, 1. The bottom row isn't going to change, so we can go ahead and fill that guy in. How about the position vector? Well, that's where we're going to have to apply a little bit of matrix operations here. In order to solve for the position vector, we're going to have to take the transpose, or rather minus the transpose of our original rotation matrix. So minus transform from A to B, or the rotation from A to B transpose, times the position vector from A to the origin of B. And so we have cosine of 30 degrees, sine of 30 degrees, 0, negative sine, 30 degrees, cosine of 30 degrees, 0, 0, 0, 1. And we're going to hit that with our position vector, 5, 4, 3. And when we do so, we see that we have 5 cosine of 30 plus 4 sine of 30 plus 0. Well, I guess I can pencil it in up here. 5 times the cosine of 30 degrees plus 4 times the sine of 30 degrees. And then we'll have the second row times the only column, so negative 5 sine of 30 degrees plus 4 cosine of 30 degrees and plus 0, and then finally a big old fat 3. Why is the z component unchanged?
Does the y component change?
Well, look at the transformation. What axis are we rotating about?
The Z.
The z. So the z component is the axis of rotation, therefore it is the component that will not change. That makes sense? So the reason why we end up with this portion is, remember, we have to undo the rotation of frame B in order to get back to frame A. This is the displacement of from frame B to frame A in terms of frame B. Yeah.
So where that 3 came from is just 0 plus 0 plus 3?
Yes.
Column. Okay.
It's 0 plus 0 plus 1 times 3 to get 3.
Oh, okay, so those are each one number for this?
Yeah.
Oh, okay.
Yeah.
I got you now.
That makes sense?
Yeah.
Okay. Now, interestingly enough, we're going to be using part of this as we go forward. In fact, this is going to be a very common attribute when we set up our model of our planer and our spatial robot. What you'll see that we tend to do is we go through and work forward or backwards through the link of the robot. And with that being said, then what we end up doing is using a while loop to increment through each of those links in order to calculate the new position of each of the different link parameters. Does that kind of make sense? So this is something that you will see pop up again relatively soon. And tomorrow we'll come in and take a look at an example with a 2-axis planar robot, just so that we can kind of see how this stuff comes into play. So with this then, we are done with chapter 2, and you guys are in a perfect place to go ahead and knock out chapter 2 assignment, get it turned in, and have 1/3 of the class out of the way. So, good? Alrighty then, so let's jump on into chapter 3. Chapter 3 starts describing the actual forward kinematics. This is all providing essentially just the groundwork to so that we can get to an introduction of the forward kinematics. Again, what was the forward kinematics responsible for? So the kinematics is just the science of describing motion and position without accounting for the forces that cause it. So what we're doing here is we're going through and looking at how the robot moves. We're not accounting for how much torque is on a joint or how much mass is represented by a link or anything like that. We're just describing the motion of this link. When we, if we were to go through and describe the true dynamics of the robot, then we'd have to really talk about the acceleration and the forces necessary in order to provide the motions on each of the joints. And that's not something that we're going to be able to cover in this class. We're just wanting to develop an understanding of how the motion occurs, not necessarily all the forces and torques and everything else that go into it. So what we can do is we can go through and review the link and joint. Link is just the semi-rigid medium that separates the joints. And the joint is the element that allows freedom of motion, or a degree of freedom. In the robot, well, in the chain, let's say. Okay, so these are two definitions we've already run into. No doubt I had a slightly different definition to them earlier on. However, these form the basis of what we're talking about next, and this is what's known as a lower pair. Any idea what I'm talking about when I describe or talk about a lower pair? When someone talks about a lower pair, what they're talking about is a joint and its subsequent link. why do you suppose we would be interested in defining a joint and its subsequent link?
Because they work together.
Well, yeah, because the joint describes the motion of the link, right? If we're looking at a particular joint, that joint is going to describe how the link that it's connected to can move, okay? Why not the previous or preceding joint? Why are we uninterested in that in terms of, or the preceding link in terms of this joint?
Because it doesn't matter, because we're already trying to figure out the direction of like the joint and the link. So
Yeah.
we're trying to find that position, so it doesn't really matter what's coming off of it.
Right, so this joint has no bearing on the link preceding it, only on the links that follow it. So if we want to go through and use this to describe the motion, then we need to recognize that this joint is only responsible for the subsequent links that follow it, most specifically the link that it is immediately attached to. And if we can come up with a way of describing that link, then we're good to go. Okay? That makes sense? Okay, so with that then, we'll go through and talk about the 6 basic types of lower pair pairs. Okay, so there are 6 types. And I would actually disagree with the author. I believe there are only 5 types, but the one type, this author and virtually every other author I looked at defined separately. So 2 of these types of lower pairs you're already aware of. What are the 2 types of lower pair devices that you're aware of?
Revolute.
Revolute. What would we be describing in a revolute lower pair as opposed to a revolute joint? If we describe a revolute joint, then all we're interested in is the rotation about that rotation of travel. When we're describing a revolute lower pair, we're describing the rotation on the joint and the subsequent displacement of the link that follows it. That makes sense? The next type of lower pair is the prismatic. Okay, how many degrees of freedom are on either of these?
1.
1, okay. Okay, the next, type of lower pair is what the book refers to as a screw lower pair. And this is why I have a hard time justifying this as a separate case. What do you suppose the characteristic of a screw is as opposed to a prismatic? It's still providing a linear displacement like a prismatic joint does. The difference is that the drive mechanism is different. So in the case of a prismatic, the way they described it is that this is a linear actuator, whereas the drive mechanism here is a screw.